Hello dear students, welcome back to the lecture series on theory of semigroups, MMTE 405. Today we are going to discuss product of semigroups. So let's define the first product of semigroups. Then we generalize this concept in categorical sense. What do we mean by actually the product? Okay. So let S and T be two semigroups. Let S and T be two semigroups. Let S and T be two semigroups. Then their Cartesian product. Then the Cartesian product S cross T, which is the set of ordered pairs S comma T, such that S is in S, T is in T. It's a semigroup. Is a semigroup where the multiplication is component wise, or you can say it's a component wise. Okay, point wise, you can also say component wise. That is S1 T1 into S2 T2 is equal to S1 S2 T1 T2. That's the product of two elements of S cross T. Then you can easily verify that it's a semigroup. One can easily verify that S cross T is a semigroup. It's a semigroup, and this is called the direct product, and is called the direct product of the semigroups S and T. It's called the direct product of the semigroups S and T. Now we give the general notion of this direct product. Now we give the general notion of direct product of semigroups. So we give a general notion. Suppose we have a family of semigroups indexed by a certain set, which may be finite or infinite. So that so here we have taken only two semigroups S and T, but in general it may be an infinite collection of semigroups. So let's take a collection of semigroups. Let I in the index set I be the collection of semigroups. Be the collection of semigroups indexed by the set I. Okay, so it depends upon I. If I suppose it consisting of only, suppose it's a set of 2 pointers, say 1 and 2, index set 1 and 2, then we have only just two semigroups S1 and S2. If I is a singleton set, say 1, then it is only it's a single semigroup S1 in that case. So it depends on I, the collection, whether it's finite or infinite, depends on the set I. If I is finite, then it's a finite collection. If I is infinite, then it will be an infinite collection of semigroups. Now we want to give the general notion of direct product of semigroups here. So let's do that. Second page. Okay. So then P, the direct product. Let's denote the direct product by P. Then P, the direct product of the family is defined of the family is defined as a set of all maps, as the set of all maps, as a set of all maps P from the index set I to the union of all semigroups. Set of all maps such that the image of I, while I is an element of the index set IP, its image of I under P is equal to is an element of for R I and IP is an element of SI. It's an element of SI for all I belongs to I. So this P, it's the product, the P, the direct product of the family defined above, family of all semigroups, is defined as a set of all maps P from the index set I to the union of these semigroups, such that IP is a member of SI. So IP means image of I under P. It should be the member of this union, and we define it like that. It's a member of SI for each I and I. IP is the member of SI. Okay. So now we define the operation on this class. So what's actually P? P is actually this. P is the set of all maps from I to union SI, I and I, such that image of I under P belongs to SI for all I in I. It's a set of all such maps. Now we define the product on P. Now let's define the multiplication of two elements. Multiplication of two elements, say P and Q of P. Multiplication of two elements P and Q of P by component wise or point wise? By component wise. Okay. What's this? I, image of I under the product is equal to IP into IQ. PQ is a map. Obviously it's a map from I to, because IP is an element of SI, IQ is an element of SI by our definition. So IP into IQ, it's again an element of SI because SI is a semigroup. So that means I of PQ is an element of SI, which means that PQ is a map from I to union SI. Okay. So then one can easily verify that this operation is associative. Then if you take three elements, say then for all P, Q, R in P, we have this I PQR is equal to, by definition, it's I of PQ into I of R. Now again apply the definition, it's IP IQ into IR. Now here they are the elements of the semigroup SI and these are the elements. IP is an element of SI, IQ is an element of SI, IR is an element of SI. So they are all elements of SI, and SI is a semigroup. So here we apply the property, associated property of the semigroup SI. It's equal to IP IQ IR, and that you can easily verify that this is equal to here. This is equal to here IP QR. So thus I of PQR is same as I of PQR for all I and I. It's true for all I and I. So thus I of PQ into R is same as I of P times QR for all I in I. For all I in I. So therefore PQ R is same as PQR. So that means this S. So that means so thus S is a, thus not S, it's P. Thus P is a P the semigroup. So now we illustrate this product for a finite indexed set I. So let's suppose that I is equal to 1, 2. We will show that this P is same as S1 cross S2. So for indexed set I, it's equal to suppose 1, 2. And suppose the semigroup, now we have only two semigroups here, let's say S1 and S2 are the semigroups, and let's suppose that I will fix the elements of S1 and S2, so, or I can and S1, then we have two semigroups. Then let's don't fix the elements. Let's write here S, then S1 and S2 are two semigroups. Here they are the semigroups here, S1 and S2 are semigroups. So now I want to show that. Now we show that. Now we show that. Now we show that this is a. Now we show that P is same as, it is isomorphic to S1 cross. Both are semigroups. We will show that they are actually same. They are isomorphic to each other. So for this I need to define a map from P to S1 cross S2. That map should be an isomorphism. So let's define map. Define map phi from P to S1 cross S2. Okay. Let's define this map by phi of any element of the product of this P. It's equal to, say, since index set I, it's consisting of two elements 1 and 2, so I will write here it's 1P, 2P, because 1P belongs to S1, 2P belongs to S2, so it's an element of S1 cross S2. So as this 1P, it belongs to S1, and 2P, it belongs to S2, because in general IP belongs to SI in general setting. So it's a map from P to S1 cross S2. So next we verify that this map is morphism. It's a semigroup morphism, and then we show that it's also 1, 1 and on 2. So first we prove that phi is semigroup morphism. It's semigroup morphism. It's semigroup morphism. It's semigroup morphism. So let's prove this. It's a semigroup morphism. So let's take two elements from P. Let P comma Q belongs to P. Then phi of PQ, by definition, it's equal to 1 PQ to PQ by definition of phi, and it's equal to, now by definition here the product of PQ, it's equal to 1, it's component wise, it's 1P 1Q, and here it's 2P 2Q. Okay, now again it's an element of S1 cross S2, and in S1 cross S2 again the product is component wise, so it's equal to this one, it's equal to, so that implies phi of PQ it's equal to IP, it's equal to IP, it's 1P, it's 1P 2P into 1Q 2Q. So that's 1P 1Q 2P 2Q, it's equal to 1P 2P into 1Q 2Q, because product in S1 cross S2 is component wise, and this one by definition is phi of P, and that it's phi of Q. So therefore phi is morphism, it's a morphism. So next property we will prove that this phi is it's 1, 1, it's injective. Phi is 1, 1. So let's prove it's 1, 1. So we choose any two elements of P, and we assume that the images are equal. Then we show that these two elements are also equal. So let's choose any two elements of P. Let P comma Q it belongs to P, such that phi P is same as phi of Q. So this implies, what's phi P? It's 1P 2P, which is same as 1Q 2Q. That's your definition. That is the definition of the product here. It's 2Q, 1Q, 1P and 2P. Okay. And this implies, since they are the ordered pairs, and two ordered pairs are equal if and only if each term, the corresponding terms are equal. So that means 1P is equal to 1Q, 2P is equal to 2Q. So which implies P is equal to Q, because P and Q, they are the maps from I. I is here set 1, 2 to union to S1 union S2, and they are equal at both the points. P of 1 is same as Q of 1, 1P same as 1Q, and they are equal at 2 also. And here domain, it is consisting of only 2 points, 1 and 2, and at every point of the domain these two maps, these two elements of the product P are equal, which implies P is equal to Q. So that means this phi is 1. Third property, phi is on 2. So let's choose any element in the product S1 cross S2. Let S1 comma S2 belongs to S1 cross S2. Then this implies S1 belongs to S1 and S2 belongs to S2. Now I can always choose a map from index set. So let's choose a map P from the set 1 comma 2 to S1 union S2. Let's define this map let P be a map defined by image of 1 in P is equal to S1 and image of 2 under P it is equal to S2. We can define this because it's a set of all maps. So this map, then this P, obviously this P it belongs to P because P is the collection of all maps from 1, 2 to S1 union S2, and it's one of the map. It's a map from 1, 2 to S1 union S2. So that's this S1 comma S2, it's equal to 1P 2P, and that's equal to phi of P. So therefore phi is on 2 because there is a P, there is an element P in the product P such that phi of P is equal to S1 comma S2. So that proves phi is semigroup morphism. It's 1 1, it's on 2. So hence it is morphism. It's an isomorphism. So therefore phi from P to S1 cross S2 is an isomorphism. So that means this product and that the Cartesian product, they are same actually. So in general, if I is equal to say any finite set, indexed set 1 to n, then we define phi from the P is the product of the S1 S2 up to Sn to the Cartesian product S1 cross S2 cross Sn by phi of P is equal to 1P 2P up to NP. So there is 1 1 correspondence between this P, the product which we have defined, and that the Cartesian product of these n semigroups.